So let me ask you actually who. Oh, the microphone. Otherwise the recording won't work. Okay, thanks. So let me ask you, who has not heard the colloquium I gave yesterday? Everybody has. Okay? Good. That will save us a little bit of time. Good to know. Now, let's just very briefly recall what we talked about yesterday. Right? So we had classical phase transitions, looked at classical ferromagnets. Here's the phase diagram, looked at the mean field theory, then saw that the actual critical behavior is actually quite different. And that's then explained by the renormalization group that leads to scaling. Here was an example of a scaling plot. And then we talked about 5-4 Landau-Ginzburg-Wilson theory. And we saw that in a mean field approximation, where we replace the fluctuating order parameter by its average, so that's just a number now, then we get an ordinary Landau free energy. And as a result, we get out a second-order phase transition with mean field critical exponents. And then we said, OK, now let's look at Gaussian fluctuations about this mean field theory. And that leads to a susceptibility that has this characteristic Ornstein-Zernike form. And the characteristic length scale here is the correlation length, which in mean field theory goes like 1 over the square root of the distance from the critical point. And so that tells us there's a diverging length scale. There are long-range correlations at the critical point. And there's also associated slow dynamics, which in the classical theory are a completely different animal. Okay, so we don't have to worry about them as long as we just want to calculate thermodynamics. And we'll get back to that point in a second. And then the last thing we did was we looked at the Ginzburg criterion, which tells us under what conditions mean field theory is likely to be a good approximation. And the answer was if we are in less than 4 dimensions, then mean field theory can never be a good approximation near the critical point because the fluctuations are just too strong. So what we did is we estimated the root mean square fluctuations and compared them to the average value of the order parameter. And we saw that near the transition, the root mean square fluctuations just blow up compared to the order parameter. So mean field theory cannot work. But for d greater than 4, it will work. Okay? And that will become important in what follows. Good. So that's as far as we got. And now, actually, only half of you were here when I asked the question. But I take it that all or almost all of you have heard my colloquium yesterday. So you've seen this figure here. Good. So let me just remind you that this is these are photographs of an actual experiment on CO2 on the critical isocore. Okay, so what happens here is the critical point is being approached on this along this dotted line. Here we are just above the critical temperature. Here we are extremely close to the critical temperature, where we see the critical fluctuations in terms of the opalescence. And here we are below the critical temperature, and you see a liquid-gas interface is forming. So here we see very directly in real space, we see the phase separation that takes place on the coexistence curve. Okay? So we have a liquid phase, and we have a gaseous phase, and they are in true thermal equilibrium. And if you want to do that with CO2, then it actually happens at an uncomfortably high pressure and temperature. So you don't want to be around when that experiment is being done. Or at least you want good shielding in place. Okay. And water is even worse, of course. Cool. So, and here just a few talking points here is that the ferromagnet, as we have seen, is in direct analogy to this liquid gas critical point. The phase diagram is actually simpler because in an HT phase diagram, the analog of the critical isocore is just flat, so it doesn't have that weird curvature. And as I showed you, the analog of the phase separation is also observed in magnets. There are tricky issues involved there that I'll come back to in my last lecture the day after tomorrow. So that MNSI experiment I showed you before, that is purported to show phase separation here. And people take that as a strong indication for the transition being first order. OK, good. Now, let's completely switch gears for a second in order to introduce another concept that I will make heavy use of later on. So we talked about classical fluids, we talked about classical magnets. Let's talk about superconductors for a second, and also liquid crystals. So in order to talk about them, we need something that's equivalent to our LGW theory here. So here M was a three-component vector. So this is an O3 Landau-Ginzburg-Wilson theory. Now the question is, what is the analogous theory for a superconductor? And here is a celebrated LGW functional for that thing, which was dreamt up by Ginzburg and Landau. They literally pulled it out of thin air. It's another one of these amazing examples in the history of science where the same thing was approached from very, very different angles. This predated BCS theory and was based on just very, very general principles. Okay? They had no idea about the microscopics behind superconductors, and just argued that quantum mechanics somehow has got to be important. So they figured it would take a complex order parameter, psi. And they said, OK, so if psi is a complex order parameter, so that's a U1 theory, which is equivalent to an O2 theory. So we need mod squareds instead of vector products. So here is a phi-4 theory for a complex order parameter. Again, parameters are T, distance from criticality nominally. We'll get back to that, a gradient squared term, and psi to the fourth term. Okay? So that would be the same theory you would write down for an XY ferromagnet, as opposed to the Heisenberg ferromagnet that we looked at yesterday. But there is a twist. And the twist is that superconductivity, of course, has something to do with the electrons in the system. And the electrons are charged. And so because they are charged, they will couple to an electromagnetic field. So Ginzburg and Landau said, OK, we had better couple our order parameter to an electromagnetic field, so to a vector potential A. And the way we should do that is so it obeys gauge invariance. Okay? So they said, let's do a minimal coupling, as we are used to from quantum mechanics, and replace the gradient here by something that makes the theory gauge invariant, and the simplest way to do that is, as you know, is to replace the gradient by gradient minus I charge vector potential. Okay. And what the charge is unclear at this point. The most natural guess would be that it was probably the electron charge. They didn't know about Cooper pairs. Because of the Cooper pairs, it turns out to be 2 times the electron charge, but that's a minor detail. Okay, and if we do that substitution, then we get the following action. We get the psi mod squared term. We get the modified gauge invariant gradient squared term. We have a psi to the 4th term. And in addition, we need something that represents the energy of the electromagnetic field fluctuations. Interrupt me anytime, please. Okay? If there's anything at all to discuss, just speak up. Yeah. Okay, so we need something that represents the energy of the electromagnetic field fluctuations. And I should emphasize, because that sometimes leads to confusion. So this vector potential here, that is not meant to represent an external magnetic field necessarily. Okay? These are just fluctuations in vacuum that are always present. Okay? So there can be a virtual field. Yeah. And what is the energy of the vector potential? Well, it's the magnetic field squared over 8 pi. So here's the curl of A squared. That's the field energy. Okay? And here's mu is a coupling constant. You can call it the permeability if you want to, but you can also just say it's a coupling constant. Yeah. Cool. So that's Ginzburg-Landau theory of superconductivity. And the historical oddity I alluded to earlier was that when BCS theory was published in, when was it, 59? Landau famously had one look at it and declared it complete garbage. Okay. So what he essentially said was, this has, number one, this has nothing whatsoever to do with my Landau theory. Okay. So that's the first reason it's garbage. Second, I look at this, it's obviously not gauge invariant. How can anybody be that stupid? Okay. So he totally dismissed it. He was, of course, one of the greatest physicists of the 20th century. But he had very strong convictions, and on occasion he was spectacularly wrong. There was one example. Another one when he declared that antiferromagnets cannot possibly exist. Okay. So anyway, Landau was correct in saying that BCS theory is not gauge invariant. Of course, Bardeen was not that stupid. Okay? He knew that. And if you look at the BCS paper, then one thing that's very conspicuous is that in a theory of superconductivity of all things, the one thing they very carefully avoid calculating is the conductivity of the superconductor. They calculated the transverse response only, which doesn't care whether the theory is gauge invariant or not. Okay. So, and then later on it was fixed up, of course, and the theory was made gauge invariant. And then Gorkov showed that the Ginzburg-Landau theory is actually equivalent to BCS theory, which is very unobvious. Yeah. Okay, so that was a historical aside. Yes? Okay, so it doesn't couple to the order parameter in any obvious way. So it was deemed to not be physically relevant for the problem. Okay. So you can add an electric field, right, and ask what the response is to the electric field. But the spontaneous electric field fluctuations, they don't couple to the order parameter in any obvious way. Whereas the magnetic fluctuations do, and they lead to the Meissner effect. Right? So that's why it's crucial to include the vector potential. But the scalar potential is not important for just looking at a superconductor in the absence of applied external fields. Okay. So now let's look at this classical field theory. Okay? Suppose ignore the coupling between the vector potential and the order parameter for a second, and look at the field energy only, right? Then the vector potential comes with a gradient only, as it does in Maxwell theory. So in Fourier space, that gradient translates into a wave number. So clearly, the correlation function of the vector potential goes like 1 over k squared. And there's a cross product here, so that leads to a somewhat complicated tensor structure. But basically, the A correlation function goes like 1 over k squared. And that, of course, reflects the fact that the photon is massless. Okay? So here we have another example of a soft mode. Okay? Here it is, 1 over k squared. And this soft mode, as opposed to the critical soft mode that we discussed yesterday, has nothing whatsoever to do with the phase transition. It's always there. It's just a property of the photon. So that's something that we could call a background soft mode, or we prefer to call it a generic soft mode. Generic because it exists in whole phases. Okay, not just at a particular point in the phase diagram. And these generic soft modes are actually, they are pretty ubiquitous. They show up in many different systems, and they are important for understanding a lot of different physics. And Thomas and Ted and I once wrote a review article that's entitled Generic Soft Modes, or something like that. Okay, now, let's look at the coupling between the order parameter and our vector potential next. So suppose we are in an ordered phase where the psi field has a non-zero expectation value. Then you see what happens. There is a psi squared a squared term. But if I look at the A sector of my field theory, that means in addition to the k squared here, I have a psi squared, a psi average squared. So a non-zero expectation value of the order parameter gives the photons a mass, okay, due to this coupling. And now let's say, well, we are really interested in what the order parameter does, and the vector potential shows up only quadratically anyway. So why don't we just go and integrate out the vector potential? That can be done exactly. It's a Gaussian integral. No big deal. Let's do it. It's question. One has to be very careful, actually, about this. Generically speaking, whenever you have a soft mode hanging around, integrating that out is usually not such a great idea. But it can give one important clues as to what's happening. And so let's do it. So let's look at our partition function, which is an integral over all degrees of freedom. That's our order parameter and our vector potential, e to our action. Okay? And if we formally perform the integral over the vector potential, then we are left with an integral over the order parameter only times e to the, I switched the sign here, sorry, e to the minus an effective action. And that effective action is obviously defined as the logarithm, modulo a sign, the logarithm of the integral over the vector potential degrees of freedom only of the original action. Okay, and my signs are screwed up here. Cool. And again, it's a Gaussian integral that we can do. Okay. So let's do it. Oh, that's the wrong one. So let's do it. And if we do that, then as you can see, something drastic must happen, because if we have a zero average order parameter, then our A field is massless. If we have a non-zero average order parameter, then it has a mass. So if we integrate out the photons, then the resulting effective action for psi cannot possibly be an analytic function of psi. Because if psi is 0, you have a divergency here. If psi is non-zero, you do not. Okay? So there must be a non-analyticity in psi. And that's not very hard to figure out what that is. If you do the integral and then expand in powers of mod psi, what happens is that you get a mod psi cubed term in your effective action. So what's happening now is, let's say we still replace the order parameter by its average. So in that sense, it's a mean field theory. But we treat the generic soft modes, which in this case are the photons, exactly. Okay. And so then we get what you might call a generalized or renormalized Landau theory with an effective free energy density that has a mod psi squared term and a mod psi to the fourth term, as it would in the absence of photons. But in addition, it's got this mod psi cubed term. Okay. And that was derived first by Halperin, Lubensky, and Ma. And they said, look, this is what's happening as a result of the photons, and we know what that does. It leads to a first order phase transition. So if you plot this free energy density as a function of mod psi, then because of the psi cubed term, it has this characteristic 2 minimum shape. And so there will be a first order transition that preempts the second order transition that you would get in the absence of coupling to the generic soft modes. Okay. So that's what's usually called a fluctuation-induced first order transition, meaning that the fluctuations actually refer to the external, the generic soft modes. That's what's meant by fluctuations. It's the fluctuations of the vector potential. And they change the nature of the order of the phase transition. They make it first order. Okay. Turns out in superconductors, so the prediction was that in a superconductor, the transition is actually first order because of that effect, not second order as was previously believed. It turned out that that is impossible to observe in a superconductor because it's a very weak effect. It happens only very, very close to the transition. Okay. You have to go to something like 10 to the minus 8 or so near the transition in order to see it, so that's not observable. Turns out there's another transition that maps onto the superconductor problem. Another classical transition, and that's the transition from a nematic liquid crystal to a smectic liquid crystal. So the nematic-smectic A transition maps onto this. What plays the role of the photons here is the Goldstone mode in the nematic phase. So the nematic phase is one where the rod-like molecules in the liquid crystal line up with respect to their direction. Okay, so it breaks the rotational symmetry, but it doesn't order them translationally. Okay. And that spontaneously broken symmetry leads to a soft mode everywhere in the nematic phase, and that soft mode couples to the order parameter for the smectic transition in much the same way in which the photon couples to the superconducting order parameter. So it's a dual theory that kills two birds with one stone, one being the superconductor and one being the nematic-smectic A transition. And as I said, in superconductors, the effect is not observable because it happens too close to the transition. And in liquid crystals, it turned out to be a very messy situation. People looked for it. They didn't see it. Transition was second order after all. Eventually, after 20 years or so of trying, they did see a first order transition in some systems. But in any case, it was not a particularly robust prediction. And that's something to be kept in mind, and we'll get back to that later on. And we need to discuss why that is. And yes?
Can you ensure that this coefficient of the cubic term turns out to be negative?
Sorry, what can be negative?
No, I mean the cubic term coefficient.
Yeah.
This has to be negative for this function.
No, it doesn't matter. I mean, if it's mod q squared, I mean, it's symmetric, right? So if it's positive, then it goes like this. If it's negative, then you get the same thing on the other side. So in any case, you can calculate that coefficient too. Okay, so. Good. And I should also mention that this fluctuation-induced first-order transition has also an interesting analog in particle physics. Alex?
Yeah. Can you say a few words on the role of the phase mode in that game?
Okay. So the phase mode is not being considered in this theory.
The reason why I'm asking is because, in principle, you could have integrated over the phase mode first, yes, and then you end up with this Higgs mechanism. So the A would have become a massive mode and would supposedly play a relatively harmless role. So somewhere there must be an error in this line of reasoning. You see what I mean?
So you want to say that the photons are never soft?
Yes, Meissner effect.
Sure.
So I take your previous action on the previous slide, integrate out the phase mode, and if I do that, A would become a massive field. I mean, it's a Meissner.
Yeah.
So then I would argue a massive field, who cares? I mean, it cannot have such a dramatic effect.
That's right.
Very good.
That's right. So if I come from, I mean, what you're saying is correct, of course, and the Meissner effect is certainly included in the starting theory. I mean, we know that. So, but what this theory is saying is that, and I think, Thomas, that's what you are saying. If I come from the disordered phase, then it says the second order transition gets preempted by a first order one. And that's still true. Right? The photons are certainly soft in the disordered phase.
Yeah. Are you? Okay.
Okay? And so then as I go into the ordered phase, now it does that discontinuously. And once I'm in the ordered phase, what you say kicks in and is true. And indeed, as Anderson pointed out, what happens then is something that's completely analogous to the Higgs mechanism.
All right. Well, thanks.
Okay.
But you can also do RP on this one.
Oh, yes, sure you can. Okay, good. Okay, good point. So, yes, if you're an RG aficionado, then that's what you would do. And if you really are an aficionado, that's probably what you would do first thing in the morning. Trouble with that is that then you get runaway flow. Okay, and now what? Okay, I mean, you may guess that that indicates a first order transition, but you don't really know that. Okay? Here is a theory that's approximate in the sense that it's still a generalized mean field theory. We have ignored order parameter fluctuations. But it's an explicit theory that tells you what happens to the transition. Okay? So the two complement each other. And actually, so after the original Halperin-Lubensky-Ma paper, there is a long paper by David Nelson got involved. So it was Nelson, Ma, Lubensky, or I can't remember who. So they actually did what you suggest, and so yes, so that was that side of the story. Yeah. Okay. And oh yes, and so the previous issue. With the phase mode and the Higgs what's now known as the Higgs mechanism, I mean that's why Phil Anderson must have been pretty unhappy when the Nobel Prize was announced 2 years ago. Okay. Yes. Yes.
So this Goldstone mode, this soft mode has to be different from the Goldstone mode associated with the symmetry breaking of the field itself.
Yes, that's right. That's right. Yes. Yes. Okay, and yet another cross correlation here is that in particle physics there is something called the Coleman-Weinberg mechanism. So that's not Steven Weinberg, by the way. It's a different Weinberg, but it's the Coleman. So what they were interested in is what they call spontaneous mass generation. So they said, let's take a field theory and tune it to be massless. So in condensed matter language, we would say tune it to the critical point. And then couple it to some gauge field. Okay? And they said, look what happens. If we do that, then the gauge field produces a mass in our massless field theory. Okay? So they were happy about that. So the particle physicists call this the very same thing, the fluctuation-induced first-order transition, call that the Coleman-Weinberg mechanism. Yeah. Good. So that's another ingredient of what we need in order to discuss what we ultimately want to discuss. So any further questions at this point? Yeah. Whenever you have a cubic term in your Landau free energy, then you see what happens, right? For small psi, it's just quadratic. Okay. So if t is positive, it's an upward curved parabola. But then the cubic term kicks in before the quadratic term kicks in. So at some point, the cubic term starts dragging it down. And then eventually, the quadratic term stabilizes it, and it goes back up. But see, here, what you can do now is for fixed v, there will be a positive value of t where the free energy looks like this, and you see now this value of psi is degenerate with that value with the zero value. Okay, and that's the first order transition. Okay? And in that sense, it preempts the second one if you come from the disordered phase. It happens at a positive t. Okay. Okay. Good. So now, time to start talking about quantum phase transition. So everything else so far was classical, including, by the way, the superconductor. Right? Of course, you need quantum mechanics in order to form a superconductor in the first place. But if you want to describe the transition from a normal metal to a superconductor, that's a perfectly classical phenomenon. It's a classical phase transition. It happens at a finite temperature. So how about what we call quantum phase transitions? Let's talk about them in general first. Okay. So as I alluded to yesterday, there are ferromagnets that have a low Curie temperature to start with. Okay, so MnSi is one, roughly speaking, zirconium, zinc 2, uranium, germanium 2, many others. Okay. And often that Curie temperature is susceptible to hydrostatic pressure. So if you apply hydrostatic pressure, you can suppress the Curie temperature even more. And when that became clear, then people got excited and said, oh, we can produce a quantum critical point. So let's see, here's a schematic phase diagram. Temperature versus, let's say, pressure. And here was the idea. So you apply pressure, and the Curie temperature, or whatever your critical temperature is, goes down. And finally, you get at 0 temperature this quantum critical point here. So then you would ask, well, so I have some idea what my critical behavior looks like here at ambient pressure. It depends on the universality class. If it's an Ising magnet, for instance, then I know what the universality class is. If it's a Heisenberg magnet, I know what the universality class is. That's all understood. Fine. So what's causing the critical behavior? It's thermal fluctuations that go crazy near the critical point. And now I suppress my transition temperature. And clearly, I still have thermal fluctuations that go crazy near the transition. So if I trigger the transition here at some fixed pressure as a function of temperature, then surely I will get the same critical behavior. But if I go all the way to 0 temperature, then I'm losing the thermal fluctuations. There aren't any anymore at 0 temperature. All I've got is quantum fluctuations. And they're very different animals. So if I trigger that same transition from the same ordered phase to the same disordered phase, or vice versa, if I trigger that at 0 temperature as a function of, let's say, pressure or some other non-thermal control parameter, then the critical behavior I observe down here, that can possibly be the same as the critical behavior I observe up here. Because the nature of the fluctuations is different. And that raises the question of continuity. So as I continuously go on this curve down to 0 temperature, how does the system manage to maintain continuity in its critical behavior? And the answer is by means of crossovers. So here these various shaded regions indicate what type of critical behavior you will observe. The answer is essentially that there is a region around the line of second order transitions where you see classical critical behavior. That's the light shaded region here. And that the width of that region goes to 0 as you go to 0 temperature. And the dark shaded regions are ones where you see critical behavior dominated by quantum fluctuations. And the medium shaded region is one also dominated by quantum fluctuations, but here you see dynamic critical behavior, and here you see static critical behavior. So it's a complicated crossover game with different regions where you see scaling behavior dominated by different fluctuations. Now, how different will the quantum critical behavior be if it exists from the classical one? Answer is, roughly speaking, pretty different. Why is that? Well, because of fundamental differences in statistical mechanics between finite temperature and 0 temperature. So to see this, let's look at a classical partition function. Hey, we have a Boltzmann factor. We trace over that. That gives us the partition function. Now, our classical Hamilton function is the sum of some kinetic energy and the potential energy. And classically, that means the partition function factorizes into a trace over the momenta only, and then a trace over the real space positions. So this is a trivial thing. Okay, that just gives you a temperature-dependent prefactor, and the action is in here. That's the one that's hard to calculate. But you don't have to worry about the kinetic piece of the energy at all in order to calculate this. So that's what we mean when we say the statics and the dynamics decouple in classical statistical mechanics. In quantum mechanics, it's very different. Formally, you write the partition function the same way. It's a trace over a Boltzmann factor. But now H is an operator, right, rather than a Hamilton function. The Hamilton operator is still a sum of a kinetic energy and a potential energy. But the trouble is that the two don't commute. Okay? And because they don't commute, this trace doesn't factorize. Okay. So in that sense, statics and dynamics couple in quantum statistical mechanics. And how to deal with this was figured out over the years. So one important mathematical ingredient was what's called the Trotter formula, which can be written in the following way. So e to the minus sum of two operators can be written as a limit. So let's take this beta seriously here. Okay, so this is some kind of a Boltzmann factor, and now if you divide your beta by n and factorize these things, and then let the limit of n take the limit of n go into infinity, while exponentiating the whole thing to the power n, then you get an exact identity. That's just a mathematical identity that can always be done. And that was used then by Kesher, Lurie, and Revson 10 years later to derive a coherent state formalism for writing the quantum partition function in terms of a functional integral. They did it for bosons initially, and then later it was generalized by Berezin to deal with fermions. So these are technical issues that can always all be looked up in books. So the result is that if you look at the Trotter formula, you take the inverse temperature, or you take the interval from 0 to the inverse temperature, and slice it into n equal intervals, and replicate in much the same way you do in the replica trick. You replicate your Boltzmann factor n times, and then let the size of your slices go to infinity, and out comes your desired trace over the Boltzmann factor. So the classical functional integral over a Boltzmann factor that involves only a spatial integral turns into the same kind of functional integral over a Boltzmann factor, which in addition to the spatial integral now has in the limit n going to infinity an additional integral over an auxiliary variable that sums up the slices from 0 to beta. Okay. And here's that auxiliary variable. It's usually called tau and referred to as imaginary time. And so in quantum statistical mechanics, our partition function is given by this expression, where the classical action is getting replaced by one that has this additional imaginary time integral. And now our order parameter field phi comes with a position dependence and in addition this imaginary time dependence. Okay. So that's just formalism at this point. There's a reason for calling it imaginary time, because if you replace tau by I tau, then you get what looks like a real-time evolution. And so that's known as a Wick rotation. And it turns out an analytic continuation actually does give you real-time or frequency dynamics from the imaginary time dependence. So it's not just a frivolous abuse of words here. It is an imaginary time in some sense. So the bottom line is that statics and dynamics indeed couple, and there's no way we can separate the thermodynamics from the dynamics of the phase transition. Okay. So now if you look at this, then naively you might say, that just looks like my classical problem in one higher dimension. Namely, in addition to the d spatial dimensions, I have the imaginary time dimension. So it looks like I've elevated my system to one higher spatial dimension. That is not quite true, because in general there is no telling how the imaginary time dependence scales with the spatial dependence. So turns out the tau can scale like length to an arbitrary positive exponent z. And so the mapping is not from d into d plus 1, but from d into d plus z dimensions. And if you tell that to an audience containing high-energy physicists, then you sometimes get the objection, but surely, ultimately, things are Lorentz invariant, and so z must be 1. And if you are telling me that z is 3, then you clearly made some stupid mistake. Okay. That argument is fallacious because of the critical slowing down we talked about earlier. So at the critical point, near the critical point, the relevant time scales go to 0. So in the renormalization group sense, what happens is the speed of light renormalizes to infinity, and therefore the Lorentz invariance argument does not hold. So Lorentz invariance truly breaks down at a phase transition. Okay. And John Hertz was actually the one who realized, who had this very important insight that z in general is not equal to 1. So what had happened is that previously, people, Suzuki in particular, had looked at spin chains. In these systems, z is indeed equal to 1. And then there was this general notion in the community that z is always 1. And then people applied the Suzuki argument to systems where it doesn't apply. And that was one of the important contributions of Hertz's paper to sort that out. Okay. Now, given that z can be whatever it is, depends on the system, then we would say now the following. Suppose our classical system had some upper critical dimension, dc plus, equal to 4 for Ising or Heisenberg ferromagnet, for instance. Okay. Then the corresponding quantum problem lives in d plus z dimensions. So the upper critical dimension for that thing will be whatever it was for the classical system minus z. So, but we know the physical meaning of dc plus is that above that dimension, mean field theory is robust. Okay. So the conclusion is mean field theory should be more robust in the quantum case because the upper critical dimension is reduced by z. Okay. So that's a very interesting insight. Essentially what happens is the fluctuations get spread out over a larger phase space, effectively. Sorry, say it again.
Z not being equal to 1.
Oh, Z, no. Z is a critical exponent. It's tied to the critical point we are looking at. So it's not dependent on how far away you are. Okay? Just like the exponents beta and gamma and nu, they are properties of the transition itself. Okay? They don't depend on how far away you are.
If one is very far away, then probably.
If you are too far away, then scaling won't work, and then the exponents don't make sense. But that's true for all of them. Okay? So you should think of Z as just another critical exponent. Okay? Just like the static ones. It has a certain value that depends on the universality class you are in. Okay.
Very far away, it will be 1.
Very far away, it doesn't make any sense to talk about it because there's no scaling.
But just look at the stable fixed point.
You can look at the stable fixed point. But that then and that has a Z in yes. But I hesitate to give that answer because I'm worried it's more confusing than illuminating. So let's stick to the transition for the time being. And then we say, okay, let me go back to this sketch here. Wait a minute, I need to get hold of AAA batteries somewhere. Okay, if we look at this here, right? So here schematically we say there is a certain region which doesn't have sharp boundaries, by the way. Okay, there's a certain region with diffuse boundaries around the transition, and in that region scaling works, and time and space are related by a certain scaling relation. If you go too far away, that just breaks down. Okay? So another way to say it is maybe a more direct way to say it is, let's go back to our classical fluid. So here we had these families of H versus M curves for the magnet. Sorry, that was the magnet example, not the classical fluid example. Okay? So here's this whole family of curves. And if you do the scaling plot, as indicated by this homogeneity law, then they all collapse onto two curves. Okay? But if you look at, you probably can't read the numbers here. So the TC for this magnet is 32.844 kelvins. Okay? And for the curve, for the scaling curve where T is greater than TC, the largest temperature they looked at was 35 kelvins. So that's some 6% away from the critical point. And the lowest temperature they looked at for the other branch was 32.469 kelvins. So that's only, what, 1% away. Okay? So, and in that region, it kind of works. If you go farther away, if you include temperatures that are farther away from the critical temperature, then they will not collapse anymore. So scaling doesn't work. Okay?
But one can still just look at the action and say that in effect one has just, because this action getting that form, integral from 0 to beta,
Yes, that's still true.
that will hold even away from the critical point.
Okay, true. So the action you can always write in this form. That's a true statement.
And then just by the appearance of it, one may say that effectively one has just added an extra spatial dimension.
No, that's not necessarily true. Depends on the dynamics. Okay? And so as Thomas says, you can describe the phase, and as I pointed out yesterday, I alluded to it in passing. You can describe the phase that describes, let's say, the ordered phase. You can describe that in terms of a renormalization group fixed point that is a stable fixed point as opposed to a critical fixed point, that stable fixed point will also come with a value of z. But that value of z will in general be different from the critical one. They have nothing to do with one another. So that the z for the stable fixed point typically in a system with a continuous broken symmetry will typically describe the dynamics of the Goldstone modes, for instance. Okay? So it has nothing to do with the critical z. Yeah.
Breakdown of scaling, is it because tau is now a compact dimension? Like tau is not. Why do we expect tau to scale in a particular way?
Okay,
with
that's
X?
that's an excellent question. So why does scaling work in the first place, right? The heuristic answer is that as people figured out over the years, studying phase transitions is just you observe that magically near phase transition scaling works. Okay? That's what Ben Widham found out and many others. And then slowly it became clear via the renormalization group why that is true. Okay? And that you get scale invariance and scaling laws only asymptotically close to a critical point. Okay? And the reason is this diverging length scale, the correlation length. If you don't have that, then scaling breaks down. Okay? So that's just, these things all hang together. Right? That scaling works only, that's not entirely a true statement, but this type of scaling I'm describing here, that works close to a transition. Okay? You can make scaling work in a slightly different sense at different types of fixed points. Okay? But this type of critical scaling works only near a transition. And if you go away from that, then tau and x have nothing obvious in common. Which one is this? That's mine. Okay. Where were we? Here. Yes. Okay. Okay. Cool. So here is an expectation now that if we look at a transition that has a classical counterpart, and that may or may not be true. Okay, the magnetic transition obviously has a classic counterpart. Metal insulator transitions tend not to. But if they do, then we might say, oh, our simple mean field theory just might get better. Okay, so it may be just much easier to deal with the quantum phase transition than with the classical one. Which brings us to the history of the quantum ferromagnetic phase transition. And let's restrict ourselves to metals, because that's where all these interesting materials are, and ignore insulators. Okay. So the history of the quantum phase transition actually goes back to Stoner in 1937. What Stoner did is he derived a kind of Weisse-ish theory for itinerant ferromagnets. And by itinerant, we mean metallic magnets where the conduction electrons themselves cause the magnetism, as opposed to other magnets where the magnetism may come from electrons in a different band, and then you have conduction electrons separately. So Stoner said, let's look at itinerant magnets, as iron, nickel, cobalt are, and do a mean field theory. Okay? So he didn't formulate it this way, but today we would say what he did was he looked at the susceptibility, wait a minute, okay, and did a random phase approximation for the susceptibility. So he summed bubble diagrams And then the rest susceptibility is the bare one divided by 1 minus a coupling constant gamma times the bare susceptibility. And the bare susceptibility is just the one for non-magnetic electrons. For zero wave number and frequency, that's just the density of states at the Fermi level. And more generally, as a function of wave number and frequency, it is in a simple approximation the Lindau function for non-interacting electrons. And gamma is the relevant interaction constant. That's the one that couples spin density to spin density and causes the magnetism in the first place. Yeah. So now we know that the little t, the parameter that describes the distance from the critical point in our Landau theory, that is the inverse susceptibility. So let's plug that in. If I ignore wave number and frequency, then the susceptibility is chi naught, which is NF, over 1 minus NF gamma. So its inverse is 1 minus NF gamma. And so if that thing is equal to 0, then I'm at the transition. That's my non-thermal control parameter. So what it says is for no interaction between the spin density, gamma equal to 0, T is 1, I'm in the paramagnetic phase. But as I crank up gamma, when gamma becomes on the order of an inverse density of states, then I get a transition. So that's how Stoner theory works. And it works equally well for the quantum case, zero temperature, and the classical case, finite temperature. It doesn't make a difference to Stoner whether you're at zero temperature or not. And then many years later, Moria and collaborators developed an elaborate theory of itinerant ferromagnets. And Moria wrote a book about it. It's called Spin Fluctuations in Itinerant Ferromagnets or something like that. So today we would characterize that as a self-consistent one-loop theory. But it doesn't matter. That's just a technical detail. So it's also a mean field theory of some sort, but a more elaborate and fancier one than Stoner's. And they got a lot of very interesting results out. And then, so that happened in the early 1970s. And then Hertz in '76, he had a broader goal. He wasn't interested in quantum ferromagnets per se. He was interested in developing a renormalization group approach to quantum phase transitions in general. So he wanted to take Wilson's RG and make it work for the quantum case. And that's what he did, and found out that Z is not equal to 1 in general. And he used the metallic ferromagnets as his prime example. So he said, OK, let's take what Stoner did and apply our new formalism to that problem and see what happens. And then later, Andy Millis looked at the temperature scaling in Hertz's framework in more detail and fixed up a few things that had gone wrong in Hertz's original paper. And when that was all said and done, it turned out that the renormalization group approach by Hertz and Millis actually reproduced almost all of the results that Moria had obtained by different methods before. So that's an interesting observation in 3 dimensions. In 2 dimensions, there were some deviations, but in 3 dimensions, it worked just fine. So that's an interesting observation. Again, Moria essentially did a mean field theory, and the RG reproduced these mean field results. So why is that? That's not true for the classical ferromagnet, as we saw. Right? The true critical behavior, as correctly described by the renormalization group, is very, very different from the mean field critical behavior. Yeah. So with 40 years of hindsight here, we can easily quote-unquote derive Hertz's action and see why that's the case. So here's a plausibility argument. Let's look at the Landau free energy again. That's always our starting point. Okay, just here's Tm squared plus Um to the 4th minus Hm. In Stoner theory, you say, okay, T is 1 minus gamma NF. Okay. More generally, T is always the inverse physical susceptibility, 1 over chi. Now, what is 1 over chi in general? Let's do RPA again, but this time let's take the k and omega dependence seriously. So in Stoner theory, we replace chi inverse just by a constant. If we take wave number and frequency into account, then it gets a bit more complicated. We have a spin correlation function here. And Hertz said, well, the important interaction we've already taken into account. That was gamma. Okay, that's the spin density correlation interaction constant. So for the rest, it can't possibly care much. So let's just take non-interacting electrons. And for non-interacting electrons, we know what the spin susceptibility is. It's the Lindau function. And here it is. It's a constant plus a wave number squared plus what's sometimes called the Landau damping term is this characteristic mod omega over k that you get in the Lindau function when you expand in wave number and frequency. So let's take that thing, plug it in. Plug it into our Landau free energy and generalize to non-zero wave numbers and frequencies. Then we get in the Gaussian term, which was just a Tm squared. Okay, here it is. The Tm squared, that generalizes to now what? To T, that's the constant, plus the k squared, plus the mod omega over k. And all of that multiplies an m squared, and everything is now wave number and frequency dependent. And then we have our quadratic term and higher order terms and the magnetic field, which I've left off here. Okay. And here you see a characteristic frequency dependence, so that describes the dynamics of clean electrons. Okay? So that's the Landau damping term. And now let's get back to the question about what Z is, okay, and how we can tell. So see, what happens is if T is some non-zero constant, okay, then you would say omega scales as k. So in that sense, Z is 1 if you are far away from the transition. And what that represents is particle-hole excitations in the electron system that are ballistic in nature, where frequency scales as wave number. But if we tune the system to its critical point, if we put t equal to 0, then there is no constant to play against. And then you see k squared at t equal to 0. At t equal to 0, we see that k squared scales like omega over k, or omega scales as k cubed, and therefore z is equal to 3. Okay? But that works only if t is 0. So that's what this line explains here. Now, if Z is equal to 3 and the upper critical dimension for the classical ferromagnet was 4, then for quantum magnets, we get a reduced upper critical dimension that's 4 minus Z equals 4 minus 3 equals 1. So from that argument, the conclusion is that for a quantum ferromagnet, at least an itinerant one, mean field theory will work for all spatial dimensions greater than 1. And that's perfectly consistent with the fact that Hertz and Millis found the same results as Moria had found in his mean field theory. So that was the conclusion as of 1976 and many years thereafter. And it pretty much killed the field. Okay? It's boring. It's just mean field theory. There's nothing interesting with respect to critical behavior. So that was the conclusion because of this dimensional reduction. Now, yes?
So in the land of damping term, so I may have missed this. You said this could be understood in the disordered phase from clean electrons. That's a damping term. Does it also occur in the ordered phase? Will we get this?
Okay. So in the ordered phase, if we take a Heisenberg order parameter, I mean, let's say an O3 or an XY model, then of course in the ordered phase you get Goldstone modes. Okay, and they come with their own dynamics. So that's a stable fixed point that's different from the critical one. Okay, so there the dynamics are different. Okay, and in the paramagnetic phase, you have paramagnons. They come with their own dynamics. So if little t is 0, only at criticality in this theory, does omega scale as k cubed. But the Landau damping term is always there. What it does, what the effective dynamical exponent is, that's a different issue. But that term is always there. That term just reflects the fact that there are conduction electrons in the system. Okay, and conduction electrons come with this kind of dynamics. Does that answer the question? Okay. Okay. So, as it turned out, and as I explained yesterday, actually, this is not what's observed experimentally. Experimentally, it turns out that the transition not only is the transition not mean field-like, it's not even second order. Okay? So it's a radical departure from what this theory predicts. The theory says it should be continuous transition with mean field critical exponents. The experiments say the thing is first order. Okay. Provided it's clean metals. And so here are a few examples again. So we've gone through that before. So zirconium, zinc 2, MNSI, UGE2, here is that plot again. Zirconium, zinc 2, you see the discontinuous jump of the magnetization. In MNSI, you see the phase separation. And there are many, many other examples. Just to show you that that's not an empty statement, here is just one table that we compiled. And all of these things do that. Okay, so there are many, many different compounds. They are all metallic ferromagnets, and they all show this first order transition. Cool. So what on earth is going wrong? Okay, so yeah? Okay, so we had this really nice plausibility argument to derive Hertz's action. And if you want to do a better job, you can. You just look up Hertz's paper and go through it line by line. And so then you come to the same conclusion. So something really weird must be happening here. Something is not quite right. And to see what's not, I mean, to get an idea about what's not right, let's take stock and see what the ingredients are, just from the observations. So we know that the behavior is seen in systems that are very different with respect to chemical composition, crystal structure, band structure, and so on and so forth. So whatever the explanation is, it cannot possibly depend on these microscopic details. It must be something universal. So it must be a statistical mechanics explanation. It cannot be a solid state explanation, because it shows up, the same phenomena shows up in systems that are so different with respect to their solid state properties. Now, what can cause universal behavior? Well, the theory of critical phenomena gives us an idea. Universal phenomena, like the universality classes, they come from stuff that happens at long wavelength and long time scales. Okay? So we should look for low-lying excitations, also known as soft modes, okay, for a clue. What else do we know? We know that these materials that do this, they are all metals. So that tells us that conduction electrons are likely important. Now, conduction electrons, of course, are Fermi liquids. Okay? So we need to think about Fermi liquids. But wait a minute, Fermi liquids have been thought about for 50 plus years. I mean, didn't Fermi figure out everything there is to know about Fermi liquids, or Lender rather? So the obvious objection at this point is, isn't it true that we know everything about Fermi liquids? The answer to that one is yes. Everything we need to know for this purpose was actually known even long before 1976. And wasn't that built into Hertz's theory? And the answer to the second question is no, it was not. And so what I'll do in what follows is explain what was missing from that, what was known about Fermi liquids, but was missing from Hertz's theory. Let me see, how am I doing time-wise here? I've got another 10 minutes or so, Raj. Is that good? Yes, okay, cool. That'll get us through this. That's perfect. We'll discuss that in detail tomorrow. But to set the stage and give you some idea as to where we are going here, let me just build in a little spoiler here. Okay. The ultimate answer will be that what went wrong is that generic soft modes were overlooked. And what causes the first order transition is a novel type of a fluctuation-induced mechanism that in many ways is rather analogous to the original one in the superconductors and the classical liquid crystals. So the bottom line is summarized here. If you look at the spin susceptibility for a Fermi liquid again, let's look at the inverse one. Okay, so we said previously, wait a minute, inverse spin susceptibility, where is it? Here. Inverse spin susceptibility, we said constant plus k squared, Lindau function. Okay. Now, what you really should do here is you shouldn't take a Lindau function, you should take the spin susceptibility of interacting electrons. After all, the conduction electrons do interact. They are not a non-interacting fermion system. Okay. So, but then the next question is, what difference can that possibly make? Well, it makes a difference. Turns out, in an interacting fermion system, at zero frequency, the leading wave number dependence of the spin susceptibility is not a k-squared. In d dimensions, between 1 and 3 to be precise, it's a k to the d minus 1. With a prefactor that depends on the interaction constants in the Fermi liquid. And for non-interacting electrons, that prefactor goes to 0. But for interacting ones, it's non-zero. And by the way, I mean that minus sign here, so that minus sign will be important in a second. And we'll elaborate on that later on. So for now, just take my word that that's what an interacting Fermi liquid does. And in 3 dimensions, that k-squared actually indicates a logarithm. So it's really k-squared k to the d minus 3 is what it really is. And in 3D, that 0 exponent indicates a log. Now, if we just take that for granted for a second, and I'll explain where that's coming from. It's coming from soft modes in the Fermi liquid, and we'll discuss that tomorrow and so on. Let's just accept that. Now, scaling in the Fermi liquid suggests that a magnetic field scales as a wave number. That's maybe not obvious, but I'll explain that too. So then we expect the same kind of functional dependence of chi inverse as a function of a magnetic field at 0 wave number. But coming back to our mean field spirit, if we have a magnetization developing, that acts as an effective magnetic field on all the other spins. Right? So whether we have an external magnetic field or a magnetization, that shouldn't matter with respect to how things scale. So if we generalize our Landau theory and put in interacting conduction electrons in Hertz's theory rather than non-interacting ones, then we expect a term that goes like the magnetization squared, because we are still looking at the Gaussian terminal field theory, times a k squared that turns into an h squared that turns into an m squared. So in H language, it's m squared h squared log 1 over h. And if we develop a magnetization, then the effective field will be the magnetization itself. So we expect an m to the 4th log 1 over m, coming with a minus sign. I'll discuss that minus sign in detail tomorrow, or maybe the next day, I can't remember. So by this serious hand waving here, we say it's not inconceivable that we get a generalized Landau free energy that has the usual mean field form, quadratic term, quartic term, and in addition, a term that goes like m to the 4th log 1 over m. And it comes with a negative prefactor. So in this notation here, I pulled out the minus sign, so the coefficient v is positive. This is actually something that Thomas and Ted and I suggested many years ago, and it was an interesting story how we got there. And then later on, we elaborated on that quite a bit. But that is the upshot. So if any of this is true, and you wind up with a generalized Landau free energy like this, then you get a first order transition. Why? Because in between the m squared term and the m to the fourth term, there is something that acts just like an m cubed term would act in a renormalized Landau theory. Okay. So that's the short version of the story, and I'll fill in the details over the next 2 days. But the conclusion will be that in clean metals, generic soft modes that live in the fermionic sector, that live in the conduction electrons, they couple to the ferromagnetic order parameter and lead to a fluctuation-induced first-order transition for the quantum ferromagnet. So let me stop here and take questions, and then we'll continue tomorrow. There are particle hole excitations in the Fermi liquid. And so what happens at 0 temperature is you get these ballistic modes where the frequency scales as the wave number. If you look at 4 fermion correlation functions, things that go like psi bar, psi bar, psi, psi averaged. Okay. Now you need to decorate these things with wave numbers and frequencies and some of them. Then you find that in any Fermi liquid, there exist excitations of that sort, 2 particle excitations that are soft at 0 temperature. Okay. But at a non-zero temperature, they acquire a mass because of the inelastic scattering between the electrons. And that's important because we want a Fermi Landau free energy like this to be true at 0 temperature, but not at all temperatures. Because we know if the temperature is high enough, we don't get a first order transition. Then it becomes second order. So what happens is that a temperature cuts off this log m singularity. And what happens is, so in a finite temperature, you get an m to the 4th log 1 over m squared plus t squared, roughly speaking. So if t is large enough, then so in suitable units, m is small compared to t, you can expand and you get a regular Landau free energy again, and the effect goes away. And that's where the tricritical point is coming from. Yeah?
Can you see this log 1 correction
Directly? Okay. What you can do is you can calculate the magnetization-dependent prefactor of the Goldstone mode. Right? So if you calculate the omega goes like some m-dependent prefactor times k squared. That's the ferromagnetic Goldstone mode. And you look at the magnetization dependence of that prefactor, then the log shows up in there. So that's a way how, in principle, you could see it directly. Has not been done, to my knowledge, but that's, in principle, a way to see it directly.
Presumably you would use inelastic neutron scattering to figure out the point factor.
Yes, that's right. That's right. That's how you could do it. Yes. Yes. Any other questions?
May I make a comment?
Yeah.
So how we presented this is absolutely right, that there's this wealth of data which shows that there's something wrong.
Yeah.
But when you, Ted, and Thomas started this thing, there were not so much data. This was purely
Cool.
something that you guys knew, I mean, from theory side, and then the experiments actually started showing that you guys are.
I wouldn't disagree with that statement.
Yeah.
Now, Just, I mean, to make things clear here. That I mean, so you know, when you start something, things are never as clear as they look 20 years later, of course, right? So, for instance, one thing that led us astray early on was, I mentioned that before, was this experiment on zirconium zinc 2. Initially, there was MNSI, there was zirconium zinc 2, and
this was about it.
that was about
Yeah,
it.
that's it, yeah.
Even the UGE2 came later.
Much later.
For a while, there was the situation that said MNSI does it, zirconium zinc 2 doesn't. We had a theory that says it always happened. So we said, geez, we had better make it not happen under some circumstances. And sure enough, we did. Okay, we should never have believed these experiments because as time went on, they made better samples, became first order. And then this explosion of systems happened. So yes, initially things were not as clear. Right, so I'm really glossing over a lot of confusion here that reigned in the early days. That's absolutely true. But yeah, you're right. I mean, it was a prediction initially. Yes. Okay. Yeah.
When you were submitting the diagrams to the exponent for one of the examples in the previous slide, I guess 2 slides back.
Okay. Yeah. Let's see. And you are referring to the here.
Yeah. So when t is non-zero, then you ignore k square.
Correct.
Okay.
Okay, so when t is not equal to 0, when t is a constant, you know, then omega over k plays against t, the constant t. So omega over k must scale as a constant, so omega must scale like k, and therefore z must be 1. And that's a true statement. The k squared in renormalization group lingo is a correction to scaling at that stable fixed point.
Okay.
Okay? Okay, if there are no more questions, I'll be around, so you can ask me anytime.
So, I have a suggestion to make to the students, so that we have extended coffee breaks, and this is the time you can actually bug the speakers with all sorts of questions, technical
Technical or otherwise.
Yeah, or otherwise. And I think you should take the opportunity to do this, right? So please do.
Okay. Please bug me.
Yeah.